Hello, welcome back. I'm John, an old YouTuber. Let's try to continue. I had to stop the video because this camcorder was low on power. And I think we still need like 1 hour to read this because this is very difficult. And of course I not understand the PDF like this. I'm not educated from university in chemical science. But that's good to read something a little bit complicated sometimes, then you can understand that actually that's very complicated. You get some more respect for people study on university and people that working on researchers on university. They're spending their life to read stuff like that, and even they're reading science books and papers that's much more complicated. This is just Wikipedia, and we're going to read science papers and books that's much more complicated. So some people, they are very clever, and sometimes it's not bad to read stuff very clever, very skilled people have rights. You maybe not understand what they're writing, but you can understand it's very complicated. So much of this. But of course, if I read it many times, but I like to read the silicon. But let's look close my list of. I just made a Dennis video. Let's go back to the silicon. I don't know if, of course, I don't understand anything of this because I don't have a science degree in chemistry. So just, but we just read everything and then we find another one. So no, some people read stuff like this. That's just one. This is just the silicon. That's 200 other chemicals. That's many hundreds others, many thousands of kind of chemicals. So I cannot close the screen. Let's try to, but I need half a minute to do myself ready. No, when I start to read a PDF, I don't know what's inside, so sometimes I understand a lot, sometimes I not understand anything. I don't understand much of this because I don't have education in chemistry. I don't understand all this, I don't know what it is. Ethylene oxide, I don't know what that is. Acetone, I don't know what acetone is. I know you can, if you have some paint, you can remove paint with acetone. And pencil for painting, you can clean in acetones. I don't know all this chemicals, numbers. Isosaline, I don't know what it is. Potassium cyanide, never heard about it. So, but let's just continue. No, we have to read, it's not working now because I did click all kind of other stuff. So the next is TSMC, then the Samsung, that should be one of the world's biggest producers of CPUs and computer chips. Like this company that's many billions of dollars, they are owning fabs making computer chips and CPU. Many hundreds of billions. Most people have never heard about it. If you're asking somebody on the street what is TSMC, Taiwan Semiconductor Manufacturing Company, that's one of the world's most valuable semiconductor company. and the world's largest dedicated independent pure-play semiconductor foundry. That's one of Taiwan's largest company. So read about next.
Decompose by eliminating silylen SiH2 or SiHR as the activation energy of this process, (210 kJ/mol) is much less than the Si and SiH bond energies. While pure silenes do not react with pure water or dilute acids, traces of alkali catalyze immediate hydrolysis to hydrated silicon dioxide. If the reaction is carried out in methanol, controlled solvolysis results in the products SiH2, OMe2, SiH, OMe3, and Si, OMe4. The SiH bond also adds to alkanes, a reaction which proceeds slowly and speeds up with increasing substitution of the silane involved. At 450 degrees Celsius, silane participates in an addition reaction with acetone, as well as a ring-opening reaction with ethylene oxide. Direct reaction of the silanes with chlorine or bromine results in explosions at room temperature, but the reaction of silane with bromine at 80 degrees C is controlled and yields bromosilane and dibromosilane. The monohalosilanes may be formed by reacting silane with the appropriate hydrogen halide with an Al2X6 catalyst, or by reacting silane with a solid silver halide in a heated flow reactor SAD 27, SiH4 plus 2HCl 260 degrees C SiH3Cl plus HCl plus 2Ag. Among the derivatives of silane, iodosilane, SiH3I, and potassium silanide, Xi3, are very useful synthetic intermediates in the production of more complicated silicon-containing compounds. The latter is alkyloless crystalline ionic solid containing K and cations and SiH3 anions in the NaCl structure, and is MAdB the reduction of silane by potassium metal. 65. Additionally, the reactive hypervalent species SiH5-ecyl 27. With suitable organic substituents it is possible to produce stable polysilanes. They have surprisingly high electric conductivities, arising from sigma delocalization of the electrons in the chain. 66. Halides. Silicon and silicon carbide readily react with all four stable halogens, forming the colorless, reactive, and volatile silicon tetrahalides. 67. Silicon tetrafluoride also may be made by fluorinating the other silicon halides, and is produced by the attack of hydrofluoric acid on glass. 68. Heating two different tetrahalides together also produces a random mixture of mixed halides, which may also be produced by halogen exchange reactions. The melting and boiling points of these species usually rise with increasing atomic weight, though there are many exceptions. For example, the melting and boiling points drop as one passes from SiF3 through SiF2 to SiF2Br. The shift from the hypoelectronic elements in group 13 andelia to the group 14 elements is illustrated by the change from an infinite ionic structure in aluminium fluoride to a lattice of simple covalent silicon tetrafluoride molecules, as dictated by the lower electronegativity of aluminium than silicon. The stoichiometry, the +4 oxidation state being too high for true ionicity, and the smaller size of the silicon atom compared to the aluminium atom. 67. Silicon tetrachloride is manufactured on a huge scale as a precursor to the production of pure silicon, silicon dioxide, and some silicon esters. 67. The silicon tetrahalides hydrolyze readily in water, unlike the carbon tetrahalides, again because of the larger size of the silicon atom rendering it more open to nucleophilic attack and the ability of the silicon atom to expand its octet which carbon lacks. 68. The reaction of silicon fluoride with excess hydrofluoric acid produces the octahedral hexafluorosilicate anion SiF26. 68. Analogous to the silanes, halopolysilane SiN X2N+2 also are known. While catenation in carbon compounds is maximized in the hydrogen compounds rather than the halides, the opposite is true for silicon, so that the halopolysilanes are known up to at least Psi14F30, Psi6Cl14, and Psi4Br10. A suggested explanation for this phenomenon is the compensation for the electron loss of silicon to the more electronegative halogen atoms by pi back bonding from the filled p orbitals on the halogen atoms to the empty d orbitals on silicon. This is similar to the situation of carbon monoxide in metal carbonyl complexes. And explains their stability. These halopolysilanes may be produced by coproportionation of silicon tetrahalides with elemental silicon, or by condensation of lighter halopolysilanes, trimethylammonium being a useful catalyst for this reaction. 67. Silica. Silicon dioxide, SiO2, also known as silica, is one of the best studied compounds, second only to water. 12 different crystal modifications of silica are known, the most common being quartz, a major constituent of many rocks such as granite and sandstone. It also is known to occur in a pure form as rock crystal. Impure forms are known as rose quartz, smoky quartz, morion, amethyst, and citrine. Some polycrystalline forms of quartz are also known, such as chalcedony, chrysoprase, carnelian, agate, onyx, jasper heliotrope, and flint. Other modifications of silicon dioxide are known in some other minerals such as tridymite and cristobalite, as well as the much less common coesite and stishovite. Biologically generated forms are also known as xelgua and diatomaceous earth. Vitreous silicon dioxide is known as tektites and obsidian, and rarely as leucatellarite. Some synthetic forms are known as ketite. Opals are composed of complicated crystalline aggregates of partially hydrated silicon dioxide. 69. Quartz. Quartz. Agate. Agate. Tridymite. Tridymite. Cristobalite. Cristobalite. Coesite. Coesite. Most crystalline forms of silica are made of infinite arrangements of SiO4 tetrahedra, with Si at the center, connected at their corners, with each oxygen atom linked to two silicon atoms. In thermodynamically stable room temperature form, quartz, these tetrahedra are linked in intertwined helical chains with two different SiO distances, 159.7 and 161.7 pm, with a SiO-Si angle of 144 degrees. These helices can be either left or right-handed, so that individual quartz crystals are optically active. At 537 degrees C, this transforms quickly and reversibly into the similar quartz, with a change of the SiO-Si angle to 155 degrees but a retention of handedness. Further heating to 867 degrees Celsius results in another reversible phase transition to tridymite, in which some SiO bonds are broken to allow for the arrangement of the SiO4 tetrahedra into a more open and less dense hexagonal structure. This transition is slow and hence tridymite occurs as a metastable mineral even below this transition temperature. When cooled to about 120 degrees Celsius, it quickly and reversibly transforms by slight displacements of individual silicon and oxygen atoms to tridymite, similarly to the transition from quartz to quartz. Tridymite slowly transforms to cubic beta. Cristobalite at about 1470 degrees Celsius, which once again exists metastably below this transition temperature and transforms at 200–280 degrees Celsius to cristobalite via small atomic displacements. Cristobalite melts at 1713 degrees C. The freezing of silica from the melt is quite slow, and vitrification, or the formation of a glass, is likely to occur instead. In vitreous silica, the SiO4 tetrahedra remain corner-connected, but the symmetry and periodicity of the crystalline forms are lost. Because of the slow conversions between these three forms, it is possible upon rapid heating to melt quartz, 1550 degrees Celsius, or tridymite, 1703 degrees Celsius. Silica boils at approximately 2800 degrees Celsius. Other high-pressure forms of silica are known, such as coesite and stishovite. These are known in nature, formed under the shock pressure of a meteorite impact and then rapidly quenched to preserve the crystal structure. Similar melting and cooling of silica occurs following lightning strikes, forming glaciolate tellerite. W-silica is an unstable low-density form involving SiO4 tetrahedra sharing opposite edges instead of corners, forming parallel chains similarly to silicon disulfide, Cis2, and silicon disulfide, Si-Se2. It quickly returns to forming amorphous silica with heat or traces of water. 70. Condensed polysilicic acid. Silica is rather inert chemically. It is not attacked by any acids other than hydrofluoric acid. However, it slowly dissolves in hot concentrated alkalis, and does so rather quickly in fused metal hydroxides or carbonates, to give metal silicates. Among filaments, it is attacked only by fluorine at room temperature to form silicon tetrafluoride. Hydrogen and carbon also react, but require temperatures over 1000 degrees Celsius to do so. Silica nevertheless reacts with many metal and metalloid oxides to form a wide variety of compounds important in the glass and ceramic industries above all, but also have many other uses. For example, sodium silicate is often used in detergents due to its buffering, saponifying, and emulsifying properties. 70. Silicic acids. Adding water to silica drops its melting point by around 800 degrees Celsius due to the breaking of the structure by placing SiO-Si linkages with terminating SiO groups. Increasing water concentration results in formation of hydrated silica gels and colloidal silica dispersions. Many hydrates and silicic acids exist in thermos dilute of aqueous solutions, but these are rather insoluble and quickly precipitate and condense and cross-link to form various polysilicic acids of variable combinations following the formula SiOx O42X N, similar to the behavior of boron, aluminium, and iron, among other elements. Hence, although some simple silicic acids have been identified in dilute solutions, such as orthosilicic acid SiO4 and metasilicic acid SiO2, none of these are likely to exist in the solid state. 70. Silicate minerals. About 95% of the Earth's crustal rocks are made of silica or silicate and aluminosilicate minerals, as reflected in oxygen, silicon, and aluminium being the three most common elements in the crust. In later 71, measured by mass, silicon makes up 27.7% of the Earth's crust. 72. Pure silicon crystals are very rarely found in nature, but notable exceptions are crystals as large as to 0.3 mm across found during sampling gases from the Kudruvy volcano on Iturup, one of the Kuril Islands. 73, 74. Silicate and aluminosilicate minerals have many different structures and varying stoichiometry, but they may be classified following some general principles. Tetrahedral, SiO4, units are common to almost all these compounds, either as discrete structures, or combined into larger units by the sharing of corner oxygen atoms. These may be divided into nesosilicates, discrete, SiO4, units, sharing no oxygen atoms. Typical coordination of metal cations in silicates, ionic radii in PM, 71, CN4 Li, 59, BII, 27, Alii, 39, PsiIV, 26, CN6 Ni, 102, MgII, 72, Alii, 54, TIV, 61, FEII, 78, CN8Ki, 151, CAII, 112, CN12Ki, 164. Sorosilicates, discrete, Si207, units, sharing 1, cyclosilicates, closed ring structures, and inosilicates, continuous chain or ribbon structures, both sharing 2, phyllosilicates, continuous sheets, sharing 3, and tectosilicates, continuous three-dimensional frameworks, sharing 4. The lattice of oxygen atoms that results is usually close-packed, or close to it, with their charge being balanced by other cations in various different polyhedral sites according to size. 75. The orthosilicates Me2 SiO4, M equals B, Mg, Mn, Fe, Zn, ANS show 4 are nesosilicates. B2 SiO4, phenacite, is unusual as both BET and PsiIV occupy tetrahedral 4 coordinated sites. The other divalent cations instead occupy 6 coordinated octahedral sites and often isomorphously replace each other as in olivine, MgFeMn, 2 SiO4. Zircon, ZSO4, demands 8 coordination of the ZiV cations due to stoichiometry and because of their larger ionic radius, 84 pm. Also significant are the garnets, Me3MiI2, SiO4, 3, in which the divalent cations, for example Ca, Mg, Fe, are 8 coordinated and the trivalent ones are 6 coordinated, for example Al, Cr, Fe. Regular coordination is not always present, for example, it is not found in Ca2 SiO4, which mixes 6 and 8 coordinate sites for CaII. Sorosilicates, involving discrete double or triple tetrahedral units, are quite rare. Metasilicates involving cyclic, SiO3, N, 2N units of corner-abutting tetrahedra forming a polygonal ring are also known. 71. Chain metasilicates, SiO2-3, infinity, formed by corner sharing of an indefinite chain of linked, SiO4, tetrahedra. Many differences arise due to the differing repeat distances of conformation across the line of tetrahedra. Our peak distance of 2 is most common, as in most pyroxene minerals, but repeat distances of 1, 3, 4, 5, 6, 7, 9, and 12 are also known. These chains may then link across each other to form double chains and ribbons, as in the asbestos minerals, involving repeated chains of cyclic tetrahedron rings. 71. A typical zeolite structure layer silicates, such as the clay minerals and the micas, are very common, and often are formed by horizontal cross-linking of metasilicate chains or planar condensation of smaller units. An example is kaolinite, Al2O, 4Si2O5. In many of these minerals cation and onion replacement is common, so that for example tetrahedral PsiIV may be replaced by Alii, octahedral Alii by MgII and O by F. Three-dimensional framework aluminosilicates are structurally very complex. They may be conceived of as starting from the SiO2 structure, but having replaced up to 1/2 of the Cl atoms with Alii, they require more cations to be included in the structure to balance charge. Examples include feldspars, the most abundant minerals on the Earth, zeolites, and ultramarines. Many feldspars can be thought of as forming part of the ternary system Nal Psi 308 Cor C 308 Ca Al 2 Psi 208. The lattice is destroyed by high pressure, prompting Li to undergo 6 coordination rather than 4 coordination, and this reaction destroying feldspars may be a reason for the Mahoroi discontinuity, which would imply that the crust and mantle have the same chemical composition, but different lattices, although this is not a universally held view. Zeolites have many polyhedral cavities in frameworks, truncated cubic dihedra being most common, but other polyhedra also are known as zeolite. Cavities, allowing them to include loosely bound molecules such as water in their structure. Ultramarine saltinate silicon and aluminium